Hey guys, I hope you all are doing great. And we have an amazing session here at Cross Carnival, and we have with us Gunnar Grosch. So it's going to be really exciting. He is from Sweden and is also a senior developer advocate at Amazon Web Services. He has been working in the IT industry for about 20 years and also has developed tons of skill sets in his journey. So he has been a front-end as well as a back-end developer and operations engineer with cloud infrastructure, technical trainer, and has also taken up several management roles. He has actively been a driving force in creating techniques and tools for the chaos engineering ecosystem as well. So today he'll be taking the session on how to improve application resiliency with AWS Fault Injection, and it really seems cool. And I hope you guys enjoy it as well, as much as I do at least. So yeah, without further ado, I would like to invite Gunnar on stage, and you can take it away.
All right. Thank you very much, Sayan.
Thank you.
Great to be here, everyone. Good morning, good afternoon, good evening, depending on where you are in the world. So my name is Gunnar Grosch. As Sayan said, I am a developer advocate with AWS. And I feel quite old now with the presentation you just gave, but I've spent most of my adult life building and operating applications. And over that time, everything has become more and more complex. So thinking about how to make applications more reliable and resilient has really become an important part of what we do. So today I'm really happy to be presenting to you about this new preview service that we have been working on, AWS Fault Injection Simulator, our fully managed chaos engineering service. And if you watched Aidan Cockcroft's keynote earlier, you saw him mention it several times and also showed a bit about how the service worked. So I'm going to dive a bit deeper into that. And since you're here, you probably all know a lot about chaos engineering already. So we're not going to deep dive into what that is, but I'm going to give you some hints as to how we at AWS look at chaos engineering as well. So the agenda looks like this. I want to talk a bit about distributed systems and why chaos engineering has emerged as a great solution to help deal with the complexity and the uncertainty with these complex systems. And I'm also going to go through some of the current challenges that our customers face when they start their chaos engineering journey, and explain a bit about why they've asked us to build this managed chaos engineering service. And we'll look at how the service works and how we can use it to build more resilient applications. And then, of course, finish it off with a few demos. So stick around till the end to see the service in use. All right, so let's get started. While the benefits of distributed computing are undeniable and really has revolutionized IT, they do have some challenges. Challenges with distributed systems involve latency, scalability, reliability, resilience, concurrency, designing APIs, marshalling and unmarshalling data, the complexity of all different algorithms that we use. And as these systems grow larger and more distributed, what is often only theoretical edge cases can sometimes turn into real occurrences. So while most people, they understand that these distributed systems are complex, it's a common mistake to think that this complexity only applies to applications that have hundreds or thousands of microservices, because this is, of course, not the case. In fact, even the simple applications that we build are complex. Take, for instance, a simple client-server communication. There are a lot of steps involved to successfully complete just one single round trip. So, client puts message onto network. Network then delivers message to server. The server validates the message. The server updates its state. Server puts a reply onto network. The network delivers reply to client. Client validates the reply, and client then updates its state. So it's mind-boggling to consider all of the permutations of failure that can happen in a simple distributed system. especially over multiple requests. So imagine what it looks like for thousands or then millions of requests. And the traditional way to tackle these challenges have been testing. But as the distributed systems have grown more and more complex, as I said, testing has really reached its limits. And often we only implement tests after outages have happened in production. And of course, then, well, it's already too late. So testing, well, it is of course mandatory, and you shouldn't stop doing tests, but it doesn't apply well for distributed systems. And often it doesn't address the complexity of our production environments. It tests things in isolation, and testing really only verifies the known conditions. So tests, they answer questions like, is it what we are expecting? Or is the result of this function X? What about all of the random failures and the other weird errors that happen on networks, like the internet? How about all of the configuration limits and the drifts? What about all of the unknown? How can you test something, build tests for something you don't know yet? Some things are just really hard to test. For example, in a system where instances run out of disk space. I'm pretty sure many of you have had disk space failures in some form or another. And debugging apps that run out of disk space, well, it looks something like this. And that is a relatively common issue that happens often when there's no log rotation. And to make things even more complicated, you can get a no space left on device error when there's still plenty of space left on the device. For example, when the file system has run out of inodes because too many files have been created. And the problem with disk space failure is that it's localized and isn't something you catch during tests. So what happens when you have a disk space failure? Well, if your instance doesn't have space left to write logs, it most of the time fails fast. And that is a real issue because by doing so, it creates a backhole. Because it fails fast, it fools the load balancer into thinking that the instance is free to receive even more requests, which in turn then fail. So if we could have caught the error earlier, we could have made improvements before they become outages. And improvements such as log rotation or using a centralized log service. We could have monitoring of disk space and have some alarms when there is, say, 10% of disk space left. That would give us some time to act before the outage. And that's just naming a few. Luckily, as we know, since we're here at this great conference, there is a practice that helps us with these kinds of unknowns, and that is chaos engineering. Chaos engineering, from our point of view, is the process of stressing an application in testing or production environments by creating these disruptive events, such as server outages or API throttling. And we're observing how the system responds and then implementing our improvements. And we do that to prove or disprove our assumptions about the system's capability to handle these disruptive events. And rather than letting those happen at 3 a.m. or during the weekend and in production, we create them then in our controlled environments and during working hours. So it's important, I think, to note that chaos engineering isn't just about improving the resilience of our application, even though the title of this session is exactly that. But it's also about improving the performance and uncovering hidden issues. Something that we think is really important is to expose monitoring, observability, and alarm blind spots, and more, like improving recovery time, improving the operational skills of your organization, and also improving the culture of your organization. So when we do chaos engineering, I want to emphasize that the chaos engineering isn't about breaking things randomly without a purpose. It's about breaking things in a controlled environment through our well-planned experiments in order to build that confidence that I mentioned. The confidence in your application and in your tools, the ones you're using to withstand turbulent conditions. And we do it by following that well-defined scientific method that takes us from understanding the steady state of our system to articulating a hypothesis, running our experiments, often using fault injection, then verifying the results, and finally learning from our experiments in order to improve the system. And improvements such as its resilience to failure, its performance, the monitoring, the alarms, the operation of the system. That is the overall system we're improving. So, while chaos engineering is a great to have option, I think we know that by now, our customers have told us that they feel it is hard to get started with. Hard because currently you have to stitch different tools together. You have some scripts, you have some libraries, and stitch that together to be able to cover the full spectrum of faults you can inject in a system. And the infrastructure, the network, the application, each have different tools to do the job, whether it's a library or an agent. And customers, they often don't want to install anything extra in their applications because the more things to install equals more complexity. It's also difficult to ensure a safe environment in which to inject these faults. Ideally, you want your tools to automatically stop and roll back if any alarms are setting off. You also want these to integrate nicely with the monitoring solution you're using. And finally, some failures are simply really hard to reproduce. It's important to realize that outages rarely happen because of one single failure. It's often a combination of small failures happening at the same time or in sequence. And those failures, well, they are just hard to reproduce. So, that's why we at reInvent in December was extremely excited to introduce our new service, AWS Fault Injection Simulator. That's our fully managed chaos engineering service. It's an easy to get started with service, which then lets you reproduce these real-world failures, whether they are simple ones like stopping an instance or more complex ones like throttling different APIs. AWS Fist fully embraces the idea of safeguards, which is a way to monitor the blast radius of the experiment and then stopping it automatically if alarms are setting off. Getting started with the service is very easy, and this is something we've really put a lot of effort into since our customers have repeatedly told us that it was hard to get started with chaos engineering. So you can use the AWS Console to get familiar with the service, try things out, and then you can start using the CLI to take advantage of the templates and integrate with services and use it together with your CI/CD pipelines. The templates you create for AWS Fist are JSON or YAML files, something that you can then share with your team, and you can version control them to benefit from all of the best practices associated with code reviews as well. So you run your experiments either in sequence or in parallel. Sequences are used to then test impact of gradual degradation, like a sequence of actions to gradually increase latency, for instance. And parallel experiments, they are to test the impact of multiple concurrent issues, which, as I mentioned before, is often how real-world outages happen. Supported services right now in the preview are EC2, RDS, ECS, and EKS. And more services will, of course, follow as well. So you can create quite complex conditions that span across a large set of AWS services that you have within your application. And these faults that we're creating, they are really happening at the service control plane level. And that's unique. So an instance is actually terminated. Memory is actually being utilized, and APIs at the control plane level are actually being throttled. So it's not faking it with metric manipulation or something like that. You'll have to use extra caution when using this service. Safeguards, well, they act as our automated stop button. This is a way to monitor the blast radius of our experiment and make sure that it is contained. And the failures that we create are rolled back if alarms go off. IAM controls can also be used to control what fault types can be used and what resources that we can affect with our experiments. We can use tag-based policies. So for instance, only affect instances that has the tag environment equals test. This is the architecture diagram of the service. You can currently use AWS Fist, as I mentioned, using either the console or the CLI. And this is the AWS CLI that many of you probably are familiar with already. The console is great to get started. Try things out during, for instance, a game day with your teams. And then using the CLI, well, it can be handy for engineers using the tool, but also to automate things with your CI/CD pipelines, for instance. AWS Fist integrates with IAM, as I mentioned before, both with roles and policies. So you can be sure that only authorized parties are able to run experiments. You can also define more fine-grained controls, for example, what type of faults are authorized and on which resources. When you create your chaos experiments from the console, Fist automatically creates a template for you, a template that you then can reuse over and over again. And once you start your experiment, Fist injects failure, real failure, on your AWS resources. It is best practice to have CloudWatch Alarms monitoring your AWS resources and workloads and define some stop actions or stop conditions that will automatically stop the experiment if they change status. And finally, you will also be able to integrate your own monitoring solution if you're using something besides CloudWatch, using EventBridge in order to trigger those stop conditions. And to use the service, there are 4 components that you really need to understand: actions, targets, experiment templates, and experiments. So let me go through each of them so you know what they do and how we define them. Actions, well, they are the fault injection actions that we execute during an experiment. And they are defined using a namespace, which is AWS service name action type. And the actions, well, they include what fault type we're using, the duration for that specific action, the targeted resources that we want to use for our actions, and timing relative to any other actions if we have multiple actions in our experiment. And fault-specific parameters such as rollback behavior or the portions of request to throttle, for instance. And this is the JSON representation of an action. Here we have 2 different actions defined, a stop instances action and a wait. And if you look at the JSON, you can notice that wait is ordered to execute after stop instances. So this is a sequential experiment execution. It's worth noting that some host-level actions on EC2 instances are performed through the AWS Systems Manager agent. The SSM agent is Amazon software that is installed by default on most Amazon Linux and Ubuntu images in AWS. I'll show you that integration during one of the demos later on. Targets, well, they define one or more AWS resources on which to carry out an action. And you define targets when you create your experiment template. You can use the same target for multiple actions within the same template. And the targets, they include the resource type, the resources themselves through resource IDs or filters or tags, for instance. And then you have the selection mode. That is how many of the resources within the targets to include. That can be all or a random selection. And in this JSON representation of targets, we're using filter to target only instances that are running in one particular availability zone. But that's not the only filter here. We also use tags to refine this selection. And I'd say that it's best practice to always use tags to make sure that we're only targeting instances that are tagged with something specific. For instance, in this case, tagged with env environment equals test. So that's yet another safeguard to prevent mistakes when doing our experiments. And then we have our experiment templates. They define an experiment and are used in the start experiment request. So when we want to start our experiment, we point to a specific template, experiment template. And these experiment templates, they then include what action we want to use, what targets we're using, the stop condition alarm, that's optional, but still something that we suggest that you use. And the IAM role to use to have permission to perform this experiment, and description and tags. So looking at a template, it looks something like this. And again, you can use either JSON or YAML as you prefer for your templates. We have the name using tags, we have the description, we have the IAM role, the stop condition, the targets, and finally the actions to perform on those targets. And as I explained earlier, we can run either simple experiments, like the one on the left here, which is sequential and with very specific targets. So we have pointed out specific EC2 instances to target with our experiment. Then we have an action, and then an action that's running after the first action. Or we can create more complex experiments using a mix of both sequence and parallel execution, and use advanced filtering for your targets, like the one to the right, where we're using instances based on our tag, and we're then having multiple actions both running in sequence and in parallel. And for both, well, we have alarms set up so that we're able to then stop the experiment if those alarms go off. Finally, we have the last part, which are our experiments. And they are simply a snapshot of the experiment template when it was first launched. So look at this as your history of experiment execution. It adds information on top of the snapshot with, for instance, the creation and start date, the status, the execution ID, experiment template ID, IAM role. And these are some of the faults that we're bringing in for the preview of AWS Fault Injection Simulator. More to come now during 2021. And of course, since it is a preview, it might change as we receive feedback from you, both on what more fault injections to support and so on. And then looking at use cases, besides the one-off experiments where you do an experiment to test something specific, we're seeing many different ways that customers are using chaos engineering. For instance, a game day. It's a process of rehearsing ahead of an event by creating the anticipated conditions and then observing how effectively the team and system respond. And events for game days, well, it can be, for instance, an unusually high traffic day, a new launch, a failure, or something else. And we can use AWS Fist then to run this game day by creating the event conditions and monitoring the performance of our system. And we can also integrate AWS Fist into our continuous delivery pipeline. And this will enable us to repeatedly test the impact of fault actions as part of the software delivery process, making our chaos engineering experiments continuous by integrating in CI/CD. All right. So with that, we've talked about how AWS Fist works. Now let's put it to practice and look at some demos with some of the features from AWS Fist. And I want to start with a simple experiment in the console, and then we'll get into some that are more complicated using the CLI later on. So let's start with the first one. So this is the AWS console, and let's see, there we go. And this is the Fist console. So let's create an experiment template. We have to give the experiment template a description for our experiment. In this case, let's call it stop and start instance. We select an IAM role, a role that has the permissions to run that experiment. And then we add our actions as we talked about before. Let's give our new action a name, stop instance, and we then select the stop instances action type. We then enter the duration in minutes. Let's set it to 1 minute. We also have a possibility to set it to start after other actions, for instance, and we can specify action parameters. In this case, that the instances should start again after the experiment. So let's edit the targets for this experiment. We're choosing one specific instance in this case, and we're selecting all since it's just one. There we go. And that is that specific instance that's running in EC2. And this is where we would be able to add stop conditions. In this case, we're going to do a simple one. So we're creating our experiment template, verifying that we want to create it. And as you can see, it tells us that we don't have a stop condition. There we go. So our experiment template is created with a specific ID. And we're now able to then start our experiment. Once again, we need to verify that we want to start our experiment, as this will happen to our instances. We have the experiment template ID shown, and the targets that we had in our experiment. And now going back to the EC2 console, we can see that that specific instance that we targeted, it is now stopping. Going back to the Fist console, we can see that it's now in pending state. And our target is matching the one that we set earlier and that we saw. It's now in the pending state in the EC2 console. And there we go. Now, since that minute has passed, the experiment is completed, and our EC2 instance is then starting once again. There we go. So that's our first experiment, a basic one. Using the AWS console, we're able to then create an experiment template, run that experiment, and see straight away in the AWS console what happens to the EC2 instance. So let's then move on to the second demo. And this is, once again, a stop instance demo, where we're going to stop instances, but this time we're going to set up an alarm. And as I've said a couple of times, these alarms are our safeguards. They act as the automated stop button to then stop our experiment. So let's look at that demo. Back in the AWS Fist console, and this is the CloudWatch console. We can see that we have an alarm, network in abnormal. Right now, it's in the OK state. So everything is okay with that alarm right now. And we're getting metrics from EC2 instances in this case. So now let's update our experiment template, the one we created before, and make one change. We're adding a stop condition and choosing the alarm that we had in CloudWatch. Here we go. Let's change it to 3 minutes so that we have a bit more time for our experiment. And then let's update it. So now our EC2 instance is running right now. Let's start our experiment using that experiment template, confirming that we want to start the experiment. Let's have a look. Here we go. The experiment is running, and we can see that we have stop condition, our CloudWatch alarm. So right now, the EC2 instance is stopping. Here we go. Now it's stopped. In this case, what we want to do is then set off that alarm. So we'll do that simply by setting the alarm state for the CloudWatch alarm. And we're going to set it to alarm state using the CLI. Looking at the CloudWatch alarm once again, we can now see that the state is in alarm. Switching back to the EC2 console, we can now see that the instance has changed its state to pending, meaning that it will start again. And now it's running. Looking at the AWS Fist Console, we can see that the experiment is stopped and in a failed state because the alarm that we had set up, the stop condition, well, it went into an alarm state, meaning that our experiment failed. And so the experiment was stopped and our EC2 instance was started. So that's a look at an instance stop experiment, but with an alarm as a stop condition. So moving on then to another demo, and this is stop instance with filters and alarms. So it is a bit more advanced type of experiment. Here we go. So these are a bunch of instances that we have in our EC2 console. These are running in US East 1, but in different availability zones. So looking at one of the experiment templates that we have in JSON in this case, we can see the target section of the template. And we've set a filter to availability zone in US East 1B. So we want to filter it to instances that are specific for that availability zone. So now we're creating the experiment template based on our JSON file instead of doing it through the console. So if we now switch to the console again, we can see that that experiment template has now been created in the console. Opening it, we can see that we have a stop instances action, and we have targets with two filters. One filter is the availability zone, that it should be in 1B, and the other was a tag. So now we can start our experiment, once again using the AWS CLI instead of the console. So we're pointing to our experiment template and starting that experiment. We can see in the output that this experiment is now running. And if we switch to the EC2 console, we can see that all of our instances that were running in US East 1B are now stopping. So looking at that specific experiment, which was our snapshot of the experiment that we're running, we can see that it's in a running state and that instances are stopping. Since we had an alarm set up for this as well, we're able to set the alarm state for that specific alarm into an alarm state. So we've done that. Looking at the CloudWatch Alarm, it is now in alarm state, which means that was our stop condition for this experiment. And now the instances are starting up once again because our experiment went into the failed state. The experiment was aborted due to our stop condition. So the instances, well, they're starting again, and we're back to the previous state once again. So that was an example of how we can use different filters, and we're able to use point to specific instances based on where they're located or specific tags that they have, together with our stop condition using the alarm. And also this experiment used the AWS CLI instead of everything in the console. Next, we're going to do an experiment that's going to do CPU stress fault injection with a stop experiment. And to do this, we're going to use what I mentioned earlier, AWS Systems Manager documents, SSM documents. And they define actions that System Manager performs on our managed instances. And System Manager, they include a lot of different pre-configured documents, but we can also create our own, which is what we have here, a document that will then use CPU stress on our instances. So let's run that. So this is our template where we're pointing to specific instance, and we're going to use SSM send command. We're pointing to a specific SSM document that is called CPU stress, and it looks like this. So this is an SSM document that's going to run on our managed instance. And what it's doing is that it's gonna run something called stress ng to stress the CPU of our instance. There we go. So based on the specific CPU level we're setting and the duration, and in this case the duration is going to be 120 seconds, so 2 minutes. So let's do that. Creating the experiment template based on the JSON file that we had. Here we go. And the output. There we go. And we get an ID. And next, using that ID, we're logging into the EC2 instance we're going to run this experiment on. Checking the EC2 instance ID. Here we go. Looking at the CPU levels on that specific instance logged in. And now we're going to start that experiment using the template ID that we created. There we go. And that experiment is now started. And what it's going to do now is using the SSM agent on the instance, it's going to run that command from the document. And looking at the EC2 instance now, we can see that the CPU levels has gone from 0 to 100%. So we're using up all of the CPU on that instance. And now we're stopping the experiment. And straight away, we can see that the CPU levels go down to 0 once again. Right. So that was an example of how we're using SSM documents combined with AWS Fist. So we're able to then perform commands on that specific instance. In this case, stress ng to use up CPU. And now on to the final one, the final demo. In this case, we're going to inject API throttle errors. One important part of AWS Fist is the ability to use fault injection on the control plane level, meaning that we're able to basically do fault injection where it's previously been impossible to do these experiments. In this case, I'm going to show an example of how we can use API throttle. That can be useful when it comes to performing experiments where we're trying to reach other services. So let's start it. So in this case, we have an experiment template that's going to use Inject API Throttle error. And this is going to run on an EC2 instance. And what we're setting are different parameters. In this case, that it's going to be on the EC2 service. And we're going to throttle two different operations, describe instances and describe volumes. So those are two commonly used API commands. So we're creating an experiment based on that template. Get it right. There we go. And then starting that experiment based on the template. And we can see then in the output, logging into the EC2 instance to then see if we're able to throttle those API commands. Logged in, we can now try these commands using the AWS CLI on the instance. In this case, EC2 describe instances. Let's just check first that the experiment is actually running. It is running. And now, trying EC2 describe instances would normally give us an answer straight away. In this case, it takes a while because the CLI has built-in retries. So it's going to try 4 times. But in the end, we're getting an internal error message in return because we were unable to use that command. So then let's stop this experiment. Check that it's actually stopped. It's stopping. And try the same command again. And now we get an answer straight away, showing that the API isn't throttled anymore. So, we've talked about the challenges of distributed systems and why traditional testing isn't enough for these complex systems. How chaos engineering helps us by stressing an application. And how AWS Fault Injection Simulator makes it easy to do chaos experiments on your AWS environments. My name is Gunnar Grosch, and I am very grateful that you wanted to watch this session today. Thank you very much.
Thank you so much, Gunnar, for this session. It's a great service, and I believe all of us are really excited to explore the same. And great sets of demos, actually.
Yeah, thanks.
So I would again urge the audience that if they have any questions, do go ahead and ask the same on Slack, and Gunnar will hopefully answer the same. Also, there are great sessions coming up right next, like event-driven chaos injection and evolution in chaos engineering. So stay tuned for the same. And thank you again, Gunnar, for the awesome session.
Yeah, thanks for having me. Thanks, everyone.